student friends and physics loving people, I'm back again with a video on applications of time independent Schrodinger equation. This will be the first example of using time independent Schrodinger equation while solving for a physical system. This video will show you how the Schrodinger equation time independent can be helpful in determining the state as well as energy of the system. So let's go. So the example we are taking is a particle in a one-dimensional infinitely deep square potential well. This actually means that it's like a well where the sides of the well are infinitely deep. So there is no chance that anyone can escape out of that potential well. That's what represented by infinitely deep potential well. So the meaning for it is that we define the potential well in terms of this function px equal to 0 within the region 0 x within 0 to L, and Vx equal to infinity for x equal to 0 or greater than or equal to L. So this 0 and L are simply representing one side of the well and L on the other side of the well, and the length of the well is simply L. We can find a well on one side x equal to 0, on another side x equal to L. So defining these three regions rather, one for potential 0, that is region number 2, and another for potential infinity, region number 1, which means the left hand side of the well, and region 2, which represents the right side of the well. Okay, so we'll find the Schrodinger equation for these three regions, and it will be obvious that since potential energy is infinite for these two regions 1 and 3, so definitely there will be no wave function for these regions 1 and 3, and we'll discard the wave function for these two regions. So that's what we have right in here. The wave function will vanish in the regions x less than 0 and x greater than L because the potential energy is infinity, and this is one of the boundary conditions that we encountered while discussing well behaved wave function in the last videos. So considering the second region 2, the time independent Schrodinger equation will become like this. This simply V is 0, so that's why only E term will be there. And equation 1 is the TISC for the region number 2. Now the solution of 1 is very simple. It's simply the superposition of sine function as well as cos function, and just putting root 2 m capital E by cos by alpha square through this relation, we can write the solution like a sine alpha x b cos x, where alpha square is as defined here. So ux equal to this is the solution given by equation 2 is the solution for equation number 1. Now we have the boundary and continuity conditions at the boundaries. The boundaries are x equal to 0 and x equal to L, where the wave function vanishes, as we have seen in case of infinite potential. So exactly at the left hand side of the well, that is x equal to 0, the one boundary, the boundary condition is that u is 0 at x equal to 0, and if you put this in equation 2, we'll get a sine 0 b cos 0 is equal to 0. Since a sine 0 is giving us 0, so b cos 0 will be 0, and since cos 0 is 1, so that means b equal to 0. So 4 now leads to the condition that the two part of the wave function, one part was a sine alpha x, another b cos alpha x, this part will go to be 0 because b is 0. Now another boundary condition, another boundary, that is x equal to L, that is u is 0 at x equal to L, would give us this kind of thing, a sine alpha L equal to 0. Since 0 of a sine function means sine must be equal to n pi, where n goes from 0 to infinity, 0, 1, 2, 3, the integers. So in that case, our a sine n alpha is equal to 0, and this means that is alpha L is equal to n pi. This alpha L is equal to n pi, and this does give us the value for alpha. Alpha becomes n pi by L as given by equation 5. Here we see that b equal to 0 already is given by equation 4, and only A will be there, and that's why we are putting only the boundary condition u equal to 0 at x equal to L for the first part of the wave function, that is this a sine alpha x in equation 2. Now equation 2 in this way becomes this one, a sine n alpha n pi by capital L x is 6. This is the equation, this is the wave function, and we put a subscript here n because this wave function is depending on the number n, which is simply means integers 1 to 3. We cannot take the case n equal to 0 because in that case that ux will be 0, and this would means that our a is also 0, but a cannot be 0, otherwise the wave function will be already be 0. So to recover the condition that a is not equal to 0, we don't put n equal to 0. So simply n is equal to 1 to 3 dot dot dot. Now this a is nothing, it's a normalization constant, and we normalize the equation as we learned earlier that the normalization condition is like this. That's modulus square of un square dx modulus of un dx with the limit going from 0 to L. So when this modulus square of un square is put, we get this like, and this this would become like this. This a square will come out, and this will be like this. So this is an integration that we can do well, and to do that integration we put that sine alpha square, sine square n pi by Lx equal to half of 1 plus cos twice n pi x by L, and doing all these things after integration we find the value of L by 2 for this integration, and this gives ultimately us the value of a, the normalization constant, and it's equal to root over 2 by L as given by equation 7. So equation 6 now takes this form unx equal to root over 2 by L sine n pi by Lx, where this root 2 by L is nothing the normalization constant a. Now the wave functions given by equation 8 are nothing but they are normalized wave functions, because already you have done the normalization factor, the normalization conditions, already applied it, and find the normalized constant, normalization constants. And also these are also known as eigenfunctions, because Schrodinger time independent Schrodinger equations, as explained earlier, is as eigenvalue equation. So this wave function will be known as eigenfunctions, and the eigenvalues corresponding to this wave function will be determined later on. And we'll find that the eigenvalues will be nothing but simply there will be energies, and that energies will be recovered from the equation number 5, where we found that alpha is equal to n pi by L. If you remember that our alpha is equal to n pi by L, and alpha is equal to nothing but this twice m by e, so alpha is equal to square root of twice m e by s cos. So putting this in this equation 5, we get this relation like this, square root of twice m e by s cross n pi by L, and ultimately taking the square of these quantities, we get the energy like E n equal to n square pi square square by twice m by L square, given by equation 9. Also we put a subscript here because this E is now dependent on n, just like the wave function un, and these are simply the energy eigenvalues for the wave function given by equation 8. So equation 8 gives us the eigenfunctions, that is the wave functions, normalized wave function, and equation 9 gives us the energy eigenvalues. And also remember that since En is proportional to n square, so it represents a parabolic equations. So if you represent this energy on one axis and n on the x-axis, we'll find a parabolic variation of this quantity, because pi, s cross, twice m, L all are constant for the system. Now this is the representation of the infinite square potential, where we see that on the left hand side x equal to 0, on the right hand side x equal to L, and this is region 1, this is region 2, this is region 3, and we see that the potential is infinite here on x equal to 0, potential is infinite at x equal to L, and here on this on the sides of the well, the wave functions also vanishes. We are finding the wave function only within this region. This was the representation for a problem. And then coming back to the wave function, we see that for values of n equal to 1 to 3, the particles, the wave functions are represented like this. This is for n equal to 1, this is for n equal to 2. You can see here 2 waves here, and you can see here t nodes 1 to 3, so psi t n equal to 3, and also these are the probability densities here. This is psi 1 square, this is psi 2 square, this is psi t square. Remember, when you take the probability density, we take the modulus square of the wave function, and since we are taking the modulus of the wave functions, so all the values are positive here. All the values of the modulus square of psi is out above this level. So that means that they are having some positive values. And here we see that on some part there is on the positive side, on the negative side. So this part represents the wave functions for n equal to 1, n equal to 2, n equal to 3. And here the probability densities for n equal to 1, n equal to 2, n equal to 3. And now coming back to the practical situation of this particular example or particular case of using time independent Schrodinger equation, we can see that the quantum dot is an example of this kind of application. And it's a quantum dot, as we know, is a crystal, and it's a semiconductor type of crystal, and having a size of this in the nanometer range, and it has free charge carriers having quantum confinement in all the three directions. So since it's a confinement, so that means that it's like the particles are within a well of infinite square potential well, and also since the dots have a dimension of 2 to 10 nanometer or 10 to 50 atoms in diameter, and so the quantum dots are intermediate between those of bulk semiconductors and of discrete molecules, and they have the properties like band gap, emission and absorption spectra, etc. So depending on sizes, these kind of things that they show, and having this quantum confinement, we can see that we can find it that quantum dot is an example of particle within a infinite square potential box. Now that because of the confinement, that the free charge carriers and discrete spectrum are of the quantum dots are comparable to atoms, but the confinement potential not necessarily show the spherical symmetry. That is the only thing that we can find the difference between those of in case of atoms and as well as in case of quantum dots. And also their moment space is larger for them for the moment, and they thus produce a very important content in the physics, because they have wide variety of applications like solar cells, LED, diode laser. So let's now understand the case of this particle in a box in terms of quantum dots. The way is that we can treat this true particle in as this like that real world particle in a box system, or a free charge carriers, basically electrons remaining confined within the semiconductor. So the reason behind that, we say that quantum dot is an example of this particular application of time independent Schrodinger equation, is that the electrons are confined within the semiconductors, just like some barriers on the two sides or two or the three dimensions, they have been blocked, and that's why they resemble the case of this particular application. Now the energy of all this quantum dot can be calculated like this expression: AC square 8R square m star xnl, where these are the effective masses, where this is a concept in solid state physics, and R is the radius of the quantum dot, and this xnl are simply the spherical Bessel function having a value of this pi for n equal to 1, l equal to 0. So for this particular state n equal to 1 and l equal to 0, that is the ground state, the energy of the quantum dot is this. And regarding that quantum dot as a true example of this case, our conception is that a quantum dot remains confined within the semiconductor, and because of that confinement, we can treat them as an example of a particle within a infinite square potential box. So we are left with some kind of assessment here. How can we represent the potential of a particle in that infinite square? Well, the diagram that is shown in this video. Then how the normalized wave function of a particle can be found out. That is the expression where after doing the normalization, that is for the expression for un, where a is found to be square root of 2 by l, and then 3, what we mean by energy eigenvalues, simply because it's a Schrodinger equation. A Schrodinger equation, time independent Schrodinger equation, is an eigenvalue equation. So definitely the eigenvalues that we get are known as energy eigenvalues, and the expression that already we have given in equation number 9 there. And also that we have already discussed how a quantum dot can represent this problem as a true example for it. So with this, I'm adding up this video will help you understand how this visualization of quantum mechanics through the application of time independent Schrodinger equation came into reality, and in course of time we can develop more examples while discussing the time independent Schrodinger equations. With this, thank you very much. Keep watching our videos, and also never forget to comment on the videos. Thank you very much once more.